All right. Hello, and thank you, everyone, for joining us for today's webinar, The Path to 5G Network Architecture, eCPRI, and NGFI, sponsored by VIAVI Solutions. My name's Ben Stone, and I'm with RCR Wireless News. Please make yourself familiar with the Zoom webinar platform. To ask a question, you'll need to go onto the Q&A tab, and we'll take your questions at the end and answer live or by text. Lastly, to let you know, we will provide the webinar slides as well as the recording of the webinar to everyone who's registered here today. Now allow me to introduce our speaker for today, Reza Vaez-Ghaemi. Reza is a Senior Manager of Product Line Management with VIAVI Solutions. In this role, he's responsible for developing roadmaps and product strategies for metro and wireless test market segments. Reza has held positions in R&D, marketing, and management in telecom manufacturing and telecom test business in Germany, as well as the United States. He's received his Master of Science and PhD in Electrical Engineering from Technical University in Berlin. Now to you, Reza.
Thanks very much, Ben. Welcome, everybody. So our presentation tomorrow is about next generation fronthaul. We are going to focus on some of the evolving technologies, obviously focus on eCPRI and next generation fronthaul interface, talk about the emerging standards in that space. Many different things are happening, and the purpose is to understand what are those emerging technologies, how they relate to each other and to 5G. So with that, let's start by looking at where we are now. So if we are looking at pre-5G, what we have in traditional macro cells, what we have is obviously a backhaul link that connects the core of the network to the cell sites, usually composed of a baseband unit, which is connected to a remote radio head, also known as remote radio unit, or U or RH, typically closer to the antenna on a tower or on a rooftop. They could also be on the ground level in some cases. But in any case, these are two distinct functional units that are hooked up typically over a piece of fiber. What we have also over the let's say over the past 5 years, we have also cases where we have small cells connected to macro cells through fiber links or coaxial or microwave. Those small cells, they are also known as metro cells, picocells, nanocells, and they are self-contained units that are typically used in smaller areas, maybe in rural areas, the areas that may not have towers and line of sight and coverage, and typically serve a small number of users at any given time. This is not what we are talking about. These links are just basically also Ethernet links that are hosted by a macro cell from another site. What we are going to talk about today is mostly the fronthaul. What we have already in network for the past at least 3 years here in the US and longer in some other countries in Eastern Asia is fronthaul. So what is happening here is now we have the baseband units hosted in some central locations, or it could be in some places in basement of buildings, or in, for example, in stadiums, in equipment rooms, and then your remote radio heads are placed farther away on rooftops, towers, or street poles, in neighborhoods connected through fiber. Could be daisy chained together or just dark fiber, or we could have WDM connections that hook up these together. It could be CWDM or DWDM, depends on the density of number of radios we need and availability of fiber. So these links are typically deployed using CRAN outdoors, or some of that also indoors in distributed antenna systems. But yeah, this is what is already being discussed. So we are starting with that and then move towards what is happening or what is going to happen with 5G. So if we zoom now here on this link, the fronthaul that we have, the CPRI protocol, this is what has been deployed now actually for for a long time. It has just not been visible to many because it has been mostly contained to a cell site and was not a concern for network and transport people. But now with the CRAN deployments that we have started to see, the CPRI and the front haul is becoming much more visible and exposed to the network. CPRI is a radio, basically a transport protocol. It's very much TDM-like, that typically goes over optical. It can also go over electrical. And basically what it does, it connects the controller, that could also be known as baseband unit or digital unit, to the remote radio head, also known as remote radio unit or RE. And it's very TDM-like. It uses the concept of hyperframes that are composed of basic frames. And inside of those, we have different types of info being carried. IQ data, that's in phase quadrature. That's actual user data that we talk to in the phones or broadband service. Then we have L1 N-band that carries various types of information, for example, errors and alarms between the radio equipment and controller. Then we have also a set of vendor-specific information that are exchanged between the controller and the radio. On the top of that, what we have is this user plane. And so we are going to zoom in on this one. So if you now look at what is in the basic frame, basically what we have is usually a control plane, control board, and then most of it is IQ data block that is carrying the IQ data for our user data, right? And if we zoom that further, then what we see is a group of antenna carrier channels. So now if we look at even further here down here, basically it's a baseband signal that is carried inside of this. And what we have been able to do is by decoding this information, we can actually display that, this baseband signal, as a spectrum of the baseband signal. And we can provide lots of value to customers in terms of PIM detection and interference hunting. This is all carried inside of this IQ data. But this is not what the major topic of today is. We are going to talk about 5G. So this is CPRI, and it's great in terms of the synchronization capabilities it delivers in terms of coordination between sites. But the problem we'll face is CPRI is very bandwidth hungry. So that's what we need to solve, and we'll talk about it. Let's talk about what 5G means. 5G is not only obviously a 4G plus 1, it's not just more bandwidth, but actually it has several new applications that are going to be all supported under the same umbrella of 5G. Massive broadband is obviously given. We need more bandwidth. We always want more bandwidth. So we are talking about gigabits more here on 5G. But beyond that, we are also talking about support for critical machine type communications. This could be driverless cars and autonomous cars, remote surgery, things of that nature, tactile internet. Very, very latency critical, ultra low latency, and absolutely important. And the third set of requirements are related to massive machine type communication. So this could be smart meters, thousands of them in the neighborhood. They don't need lots of bandwidth, but they need to be able to all work with very, obviously, large number of sensors we talk about. So lots of endpoints we need to support, but also we have to make sure that the battery discharge time is extremely long. So we don't need to send people to reload the battery, and therefore battery discharge time extremely important for this type of application. So when you're looking at that, you have a three-dimensional problem that we need to solve, and we look into what are the options to solve those problems now here. So, but first, let's look at the CPRI again. So what I said was CPRI is great in terms of synchronization, coordination between sites. And I think it's going to stay with us for a long period, as long as we have 4G and 3G. But problem that we have with CPRI is when we get to 5G type of application, then it won't scale anymore. When we get to massive MIMO 5G type of bandwidth in gigabit range with 64 TX and RX, then the bandwidth you need on a CPRI link would be going above 100 gig. Then we get into a range where it becomes really expensive in terms of optical components that we need to put in radios, in terms of all the bandwidth we need to support on the front haul, WDM, etc. So it's just not going to be practical. Here I put some calculations here. When we get, basically the calculation works like that. The number of radios, in this case the sectors, the number of carriers, and then the data rate per carrier. All these are factors that contribute to the bandwidth. Also, the encoding scheme goes into the bandwidth, and if there is compression, then obviously that will reduce a little bit the bandwidth. But all these factors go into the end band number, basically the product that is then necessary to support the bandwidth. So you see, it's not practical anymore. Even here, medium-term TD-LTE is going to reach some limitations. That's why we are talking about new solutions to solve this problem. So how can we solve it? If we look into a baseband unit, basically what we have at this stage, there are various number of functionalities that are in a baseband unit. We're going to just very briefly talk about them: ORC, PDCP, RLC, MAC, and PHY. And the only component really at the end, functionally, that is in the radio is this RF functionality in there. The beauty of that is we can put all these baseband functions in one place and just have a very basic dumb kind of radio all over the antenna. We can coordinate all these radios over this interface, which is CPRI, basically option 8. We can centralize, pool these resources. So that's why CRAN is so successful, because we can do all that. However, the problem is this interface is very bandwidth intensive. So people started looking into what can we do to reduce the bandwidth here and at least keep some level of functionality in there. When we looked at the options, there were 7 options at the high level that were identified to do that functional split. Basically splitting the function, putting some more functions into the radio, and obviously less on the baseband part. Over time, people realize it's not practical to have all 7 options in the ecosystem. It becomes just too expensive, too many interoperability problems. So we are been looking into some basically compromises over the past year or so to maybe narrow down all to few options, less than 7 for sure. And this is what has been happening. At a very high level, we are talking about at least having 1 lower layer split option and 1 higher layer split option. Why do we need 2? At least 2. Why? Because if we pick a lower layer split option, let's say here option 7, then we can still get some level of coordination, joint scheduling that are so important for our advanced mobility applications. For example, coordinated multi-point. Reduce bandwidth, but still get some kind of coordination between sites. However, if our application doesn't need that coordination, and we have a massive bandwidth application like residential applications, millimeter wave, they don't require the comp functionality, then we could look into something like option 2. Here at this option 2, we get a lot more bandwidth saving, but we won't get the benefit of comp. So this is what is going on right now, a kind of agreement on a low layer split and high layer split. And we'll get back to that in a moment towards the second half of the presentation. But let's just quickly look at these topics. Definitely, this is not the topic of today. This radio layer functions, this could be a conference for itself, and for just talking about these different layers of functionality. But I just wanted, for the benefit of this today, just to talk about the acronyms and where the standards coming from. Obviously, from 3GPP, got the 4G and then 5G reference documents here. If anybody is interested, they are public. Basically, the radio resource control is the top level that coordinates the calls that have control information, for example, notification of a terminating of a call. Lots more functions in there. I just mentioned some highlights here. So this is about resource control, radio resource control. The next layer below that is packet data convergence protocol. That's more about data transport, integrity, the compression, ciphering, those kind of functions are in that, and much more. Then we go below that, radio link control, and you've got different transport modes, and acknowledge mode, transparent mode, error correction, and we got also resegmentation and reassembly functions in that layer. We go below that, that's media access control. This deals with data transfer, the resource allocation, the HARC protocol, which is an important one for our discussion, is also in that MAC layer, and also the mapping of logical and transport channel. And then we got the PHY, a lot more happening in PHY. There are multiple standards, actually, documents that talk about the actual physical layer procedures, the measurements, how exactly the channeling, the channels work, the physical transport channels, the modulation, and the muxing and channel coding on top of that. All right, so this is just very high level talking about the PHY layer. If we actually break the PHY layer, then there are even options inside of the PHY layer that the ecosystem is looking at. So we are even talking about sub option 7. The option 7 is the PHY layer, and even within option 7, we are looking at different types of splits. We could just do a split as low as option 7 or as option. Yes, are components of the option. If we look at option 7, then the element mapping. If there is a beamforming, there are two types of beamforming. The digital part happens here, and then a very intensive part of that is actually the FFT, or the inverse FFT with cyclic prefix removal. This alone, this stage is very intensive in terms of processing, and the bandwidth is necessary. So if we can even cut a 7-1, if we can have a split here, we are already saving lots of bandwidth. However, we can even save more. We can go to option 7.2 and put the digital beamforming in the radio, or we can go here, option 7.2 or 7.3. The higher we go, again, we have the issue that the less coordination we will have between the sites. Therefore, there are pros and cons for each of these options, and are still discussion going on which ones different vendors or operators would like to pick. So today, now we are going to start with eCPRI, and what eCPRI says is the eCPRI document was released just a few months ago, end of August, and what it said was, it says they don't mandate which option we take, but they definitely recommend two options. One is for this link, that is the downlink. So downlink is from the baseband unit towards your cell phone, and uplink is up from your cell phone towards the network. And the eCPRI document says it recommends either the downlink at this layer, ID, or the 2D. And for the uplink, it recommends this option 7.2. All right, so customers can pick. Again, there are different pros and cons. We are going to zoom on that. Now, the next slide. What it says is, first slide, looking at the physical layer. Actually, the eCPRI protocol doesn't mandate what physical transport protocol is used, but it's very actually obvious in many cases that Ethernet would be the preferred choice because of the huge ecosystem that we have, and also the possibility down the road to do to take advantage of features of Ethernet, such as statistical multiplexing, gains that we can get, and all the ecosystem we have in the backhaul for transport of Ethernet. But there are also options if customers would like to use OTN. There are advantages for OTN, as we know. I've seen it in Eastern Asia, for example. If we have multiple operators using the links, multiple services, we need transparency. OTN provides a very low latency and predictable deterministic latency. We can still separate different types of traffic from each other. So that's why I think there will be also a use case for OTN in some cases, although I think majority will be still Ethernet. And then on top of OTN and Ethernet, we are also talking about things like FlexE and or FlexO, whatever. So all those things are possible, and eCPRI actually doesn't mandate which ones are taken. But here is what is in the eCPRI document. For example, Ethernet is highlighted, and what you see are different types of PHYs that can be used. Again, it doesn't say you have to use it, but it is one that would be expected to be used in volumes. I think 10 gig is given. Different types of optics, depending on the type of bandwidth we need and the reach, depend on the reach actually, and obviously the cost that we can afford for that application. 25 gig is coming. The 25 gig is already in data centers, and what we are seeing is now as optics become available for 10 kilometers and with FEC or without FEC, doesn't matter. We have optics that are now becoming available that can go for the distances we need for front haul, several kilometers. So this is happening now. 40 gig is also available in data centers and also as LR4. Of course, one has to look into that. We start to see 40 gig is a QSFP already, but many things that I see in the field may use actually a QSFP with CPRI rate 8, basically 4 wavelengths, each carrying a CPRI rate 8 signal. So actually not a 40 gig Ethernet. The optics 40 gig big actually doesn't care at the end. It carries either 4 wavelengths or 4 fiber as MPO carried all in a bundle, right? So that is the 40 gig piece. Also, again, possible in eCPRI, and finally eCPRI at 100 gig. These are some of the optics, but people may also look at optics for data center applications if they want to save much more on optics and they don't need the reach and are okay with 100 meters or 500 meters, then we can go even PSM4 or CLR4, SWDM. Those are all possible. Again, eCPRI doesn't say which ones you use, but it mentions this here in the standard body. Very important, obviously, to transport SLA is very stringent, and that's why we are going to talk about the split options and what type of traffic can be carried, how traffic can be managed, should be managed in the transport network to reach and to meet these SLAs that we have. So when we look at eCPRI, actually eCPRI has defined already an ESA type. This is the ESA type that is in the eCPRI spec. And then it provides for different message types that can be carried inside of that Ethernet pipe, I say Ethernet flow, right? So you can have ESA message types, for example, IQ type data, bit sequence, and real-time control data. So if you are at a split option E, this split option E, if you remember before, it was actually CPRI, then you are carrying a time domain IQ. But this is not what is in eCPRI. eCPRI recommends options 1U or 1D or 2D. If you are at option 1 uplink or downlink, then you are using IQ data in a frequency domain IQ data. It's not time domain IQ data. If you are using option 2, basically in the downlink, then you are using actually the bit sequence here. That's the option 2D. Pros and cons for each. We won't have time to go into the details of that, but just suffice to say that eCPRI is carrying the IQ data or the bit sequence here under these message types. The thing that has to be bear in mind is if you are carrying IQ data and bit sequence, you need also real-time control data to tell the radio how to understand this IQ data. So these real-time control data and the IQ data or the bit sequence, they go together. The real-time control data provides the context for this. Without this makes no sense to the radio. This has to go together and very tight together. And then we have other types of data that can also be carried and are carried over generic data transfers. We got, if the baseband wants to look at memory on the radio, there is data for that. This is one thing actually very interesting for us. Look at one-way delay measurements. There is actually a standard of enabling one-way delay measurement, since we know one-way delay is so, and since CPRI and radio traffic is so delay sensitive. So there is actually a provision for measuring one-way delay here in eCPRI. Can do reset, event notification, and of course, as usual, always some vendor-specific and reserved bytes for vendors' purposes. So now, if we go one further step here, what eCPRI service eCPRI says is actually it focuses on eCPRI services, which are the user data, the real-time control, and these other eCPRI services I had in the previous service. It does not actually mandate what CNM, synchronization, or connection OEM are used. If customers want to use Ethernet OEM, they want to use PTP, they want to use whatever SNMP, is all up to customers to decide. This is not in eCPRI standard. eCPRI will talk about these protocols, the eCPRI services. And it says, like I said, you can use Ethernet, it can be layer 2, or it can be layer 3 and 4. Also, I would expect majority will be layer 2. Again, depends on customers' network, whether they go through a routed network, third-party network, or is it a layer 2 type of network. They can use both with VLANs, etc. So this is the eCPRI, basically, protocol. All right, so now that we covered the eCPRI, I'm going to switch over. This is the eCPRI part of it, but eCPRI is not the only game in town. We have had lots of activities in ITripleE over the past 2-3 years, at least, on this front haul. And what do we need to do to enable the transport for these so delay sensitive and jitter sensitive front haul and for radio? That's why the ITripleE I221 working group CM was formed several years ago to look into that, to see how we can use the bridged Ethernet network. I221 is for Ethernet network, Ethernet bridge network, right? So they developed this working group to look into a network that can carry timing sensitive front haul, TSN also front haul. What is in A221 CM is basically the requirements for latency and frame loss ratio and jitter. It defines different classes for CPRI, which is option 8, and option 7 eCPRI, and then you have the latency. Really, it depends your latency if you are carrying IQ, CN, or synchronization. As usual, synchronization is the most demanding for timing measurements and timing SLAs. IQ is less dependent, stringent on the timing and the jitter, but still has a very high latency requirements, a high stringent latency requirements, 100 microsecond. Frame loss ratio is given. CNM is the least demanding, still out there. So therefore, when we look at SLAs for these networks, it's important to distinguish between 3 things. One is, what is our option in terms of functional split? The second factor that goes in is, what kind of traffic are we carrying? And the third factor is this: if you are carrying synchronization over your network, then your SLA is also determined by what type of wireless requirement you have. If you have a 4G type of TDD network, then your requirement is less demanding. This is like the current backhaul 1.36 microsecond LTE TDD. If you need carrier aggregation, interband carrier aggregation, then it becomes much more stringent. You're into 110 nanosecond. Now, if you get to intraband CA, contiguous carrier aggregation, then it gets more. And then if with MIMO transband diversity, we get into 10 nanosecond. These are all defined in the 802.1cm and other related standards. So you see, things get quite interesting when we go to these applications. And so that's why the ecosystem carefully looking into that and developing new standards and new chipsets to be ready for deployments of these type of front-haul services. Now, the 802.1cm also defines profiles. It says for class 1 and class 2 user plane, defines profiles A and B. Profile A and B both can be taken. Profile A is relies on a strict priority queuing with this frame size, and obviously highest class IQ is the highest priority class. It can work. The frame profile B is even more powerful, but requires additional features. This is frame preemption that is provided in 802.1 BU and BR standards. And this alone, it could be and will be another webinar for sure, or webinar series, the whole TSN. We won't have time for it. Anyway, the summary of that is that profile A and B both are provided in 802.1cm that can work for class 1 and class 2 user plane, basically for eCPRI and for CPRI type of traffic. Now, so this is the scope of 802.1cm, but 802.1cm doesn't say how you solve the problem. Now we get to another standard that talks about some of the options. ITripleE 1914.1 was formed several years ago as well, and basically looking packet-based front-haul transport network. Architecture is defined here for different use cases, and basically the idea is, how can I enable critical 5G use cases like massive MIMO, comp, CRAN to be transported over a packet-based transport network, right? So it defines architectures, a unified management control plane, and really at the end, the top goal is we got a safe bandwidth, right? This is the reason we need this, otherwise we could live with CPRI. How can we scale it? How can we reach these sync performance goals that we had in the previous slide that we got talking about sub-microsecond synchronization performance, and also obviously support cooperative radio modes, comp, etc. This is the goal from very high level of the ITripleE 1914.1. So what it says, it defines different types of interface, next generation front-haul interfaces. As usual, we need multiple options because we got to solve different problems that have different requirements. So NGFI 1 basically is an interface that would work with a lower layer split. Can also be known as a lower layer split, or one implementation could be eCPRI. Basically, in this implementation, what we do, we put the low-fi in the radio, and then the other protocol stacks go in here in the distributed unit, which could be co-located with central unit. And then from here is the backhaul that goes to the next-gen core or to the LTE EPC, basically the core, evolved packet core. So that's the backhaul. We're not focusing on that today. So this could be an architecture that you can use NGFI 1, right? The other option is we could put more of the components and functions in the radio. Basically, the distributed unit go in the radio, and then you have NGFI 2. And you have RRC and PDCP still in the central unit, and eventually, hopefully, this will be virtualized, and that gives us a lot more advantages. But yeah, virtualization also can be another topic for another webinar. The third option is we could have a double split. So then you have this kind of architecture. So why do we need this? Because we are trying to solve different problems and use cases. And so, for example, if you have a massive MIMO type of macro base station application that you want to solve, this could be actually a good split here, NGFI 2, where you put most of the functionalities of the DU in the radio, and you have basically just a central unit over centralized. Right? So this could be a massive MIMO application. It could be what we now also talk about in US in terms of fixed wireless broadband or fixed wireless access, the type of applications that could replace like FTTH type application, wireless loop, right, that being deployed. These applications typically don't need that stringent, that coordination of different radios. Require huge amount of bandwidth. We are carrying now millimeter, centimeter wave type of traffic. So use millimeter wave and centimeter wave to carry 100 megabit, 200 megabit, 800 megabit in future of bandwidth to the CPE device, to our homes. So massive amount of bandwidth has to be carried over. Got beam forming going on in this, and if you have this amount of bandwidth to carry, then it really becomes important to reduce the bandwidth on this side. And that's why we put this functionality in the radio, so we can cut the bandwidth here. We're talking factors of 20, 30 more that we can save by putting all these functionalities here in the radio. So still, we got time alignment error. This is for the radio that needs to be observed for MIMO application. But the beauty of that is our latency is much more relaxed. We are not talking about 100 microseconds. Now we are in orders of milliseconds. That allows us to do much more. We can go into kilometers much longer. We can extend this into central offices farther away from the neighborhoods where the actual radio is connected. So at the end, really, the factor there is, or the formulas is in respective documents that are being worked on right now in the standard. And basically, the throughput you are getting is the number of the cells that you have. Your spectrum, here I was talking about 100 megabit, 200 megabit, whatever we have, I'm sorry, 100 megahertz, 100 megahertz, whatever bandwidth we have, and whatever overhead we have. All these are factors that contribute to the bandwidth that goes over this massive MIMO application. So this is the next application, is the ultra low latency and massive machine type communication. This one is a good one maybe for a double split. Our jitter requirements are obviously very stringent because we are talking about, you know, ultra low latency, driverless cars. We are very stringent in terms of jitter. But our latency is okay. Still, we are talking about millisecond type of applications. So this is an architecture that could work for this type of applications, double split. And third one, this is more our CRAN-based model. We have lots of radios. We need to do coordination. And if we have this type of coordination, then obviously we need a lower layer split. This is where eCPRI becomes kind of viable solution we need to look at. But again, eCPRI doesn't have to be the only solution. We could have other type of lower layer split. If vendors come with proposals and operators demand that we have another standard that is more flexible and more open, then other standards could become available. So lots of things going on right now between operators and vendors in that space as far as what could be solutions for NGFI 1. But at a very high level, the features that distinguish that is obviously time alignment error. This is the one you remember, the toughest synchronization requirement. 65 nanosecond or even lower. If we need diversity, transmit diversity. Your latency also very stringent. That determines, for example, your distance and what kind of equipment you can put in there. The more electronics and framing and buffering, etc. we put there, the distance gets shorter. That's why this is a very interesting topic for our time-sensitive networking discussions down the road. And in this case, basically the throughput is determined by multiple factors beyond what we had in previous slides. So the number of cells, the spatial ladder, the component carriers, compression ratio. Big factor is this one. That's why it's important to decide at the end of the day, do we need option 7.1 or 7.2? Because the FFT block size is such a huge factor that goes into that option, and the overhead, obviously. So those are the things that determine the throughput of this option. I think this will be one of the major applications that we will see in or our emerging 5G mobile applications coming down the road for example, in the upcoming Olympic Games or in Tokyo or in World Cup, for example. This could be viable solutions. So now a little bit here. So when we look at this ITripleE 1914, it actually provides different subclasses for data plane, and suffice to say, so depend on your application. Again, you could have different latency requirements. Ultra low latency is the most stringent requirement, and subclass 4 is basically our legacy backhaul, right? For CNM, again, if you are low latency, then you need high, basically stringent requirement. Otherwise, there's no requirement. It's very less relaxed. But low latency RAN on the control plane requires 100 microseconds. For sync, there is still TBD in the standard bodies that are working on that. And then the transport CNM has its own basically requirements. So, and this is the priority level. It's obvious the more stringent, the higher the priority level here that is being defined. So you can have all of that in one network. Ideally, then you have this converged heterogeneous network that brings all that together. And of course, the topic that comes along with that is the network slicing topic for itself. We can talk about it, but basically this is the concept for future, right? You can have the next-gen radio with IoT and the 4G LTE all riding over this same physical network, fiber network, even backhaul together. And that would be then the way you distinguish and manage all these different conflicting requirements is by having network slicing and prioritization control, preemption, all of that. So all that hopefully at some point in time will come together and make sure that we can have a converged network. So just for the sake of completion before I close, I want to mention also radio over Ethernet. This is not actually strictly spoken a 5G topic, but it should be mentioned because actually what it talks about in this case is about using Ethernet transport for carrying CPRI or other traffic over an Ethernet network. And the advantage of ROE is in that case, you can use your Ethernet networks. You have the scalability of Ethernet. You have the whole ecosystem of Ethernet. You can bring Ethernet together with CPRI together with your backhaul. But still, ROE is not giving you huge relief in terms of bandwidth. And you still need to deal with the CPRI delay jitter SLAs. So this standard is also approved, 1914.3. that deals with it and basically how it's mapped. There are different mapping schemes beyond the scope of the webinar today, but they are all in the standard available here to study. So summarizing here, basically 5G will introduce new services with various levels of SLAs. CPRI definitely will not scale for 5G, but I expect that to be in the networks for a long period of time. We talk about functional splits, different types of functional splits, and the solutions, the use cases. Definitely, low split options are very important for the advanced features of comp and carrier aggregation, etc. But very stringent SLAs and high layer splits options are also variable for applications like massive MIMO that can be used. All right, more information can be found in this link that I provided, or I'm sure there are much more valuable information also on the web that can be provided. And with that, I would like to close the presentation part of the webinar and hand it off to Ben for the question and answers.
Great. Thank you so much, Reza. That was a wonderful presentation. So I'd like to start with this question. Is CPRI going to go away with eCPRI and NGFI?
Yes, good next question. Thanks, Ben. So yeah, typical question that I receive and many people receive when we talk about eCPRI. And the short answer is no. And the reason I don't expect this CPRI to go away is because, first of all, it is very simple. It's known technology for a while, simple design. It enables coordination between different radios, all the coordination fixtures that is synchronized. So in that sense, it provides actually a good solution that is already working and available at good cost factor. And the other aspect to bear in mind with CPRI is this: if we talk about the 5G service deployment, initially what the 5G ecosystem is thinking of is this. They are thinking that 5G will be used in a combination with 4G. That is, you would use 4G actually to provide services for mobility and for coverage, for long reach coverage. And you would use 5G for capacity. For example, if you have an application in a stadium and you have thousands of users that want to carry a high resolution video, so you would use the 5G small cells to serve those type of applications, but you still would use the 4G for mobility application if users want to basically go in this neighborhood, obviously drive in the cars. So in these non-standalone applications, you would still use 4G. Therefore, I expect still the 4G to be around for a long period of time. And for those applications, obviously, you would still want to have, you would still have CPRI. CPRI is very cost effective. You would use that for LTE type of carriers, 20 megahertz, even 40 megahertz, lower number of MIMOs, 2x2, 4x4. All of those could still work with CPRI, with maybe even with some compression, you can get even higher order MIMOs in there. And therefore, I think that CPRI will still be with us for a long period of time.
Great. Thanks, Reza. Question from the audience. How does Metro Ethernet networks fit into the sync requirements for CRAN environments, 65NS, TE?
Right. Yes. Thank you for the question. I think that is a tough requirement, as our audience noted here, 65 nanosecond time error, a very tough one to meet when we have the backhaul network that was designed, with Ethernet switches that are, we are talking about latencies in milliseconds and jitters in, maybe in microsecond, sub-millisecond, higher order microsecond. So when we go to sub-microsecond, then things get much more challenging. Therefore, we had this idea of timing-sensitive network. This is why we need a new type of Ethernet, if you want, and new Ethernet type of switches that can get us this type of time errors, time alignment errors on the radio side. And so it will be very interesting to see what equipment will become available. Definitely chip vendors, equipment vendors working on that. Lots of activities going on in these bodies like ITripleE and XHAL and NGMN and other bodies that look into what we can do as we get into bringing together the front haul and back haul together, this XHAL network. So it will be interesting to see, but definitely the current backhaul will not be able to support that kind of SLAs like 65 nanosecond.
Great, thanks.
If you're using an Ethernet switch, if you're using OTN, I'm sorry for interrupting you,
no.
But if you're using WDM or dark fiber, this is obviously possible, but not with a switched Ethernet network. Sorry.
No, that's wonderful. Thank you so much, Reza. Next question, what will be the role of passive optical networks in the front haul using eCPRI and NGFI?
Definitely will be something that will be important. Operators looking into that at passive optical network PON, next-gen PON, also at WDM, obviously as a valid, because as we said several times here, the jitter requirements are so stringent that that the current Ethernet-based net technology won't work. So there are then you have two options left at the end of the day, or maybe three options really at the high level. One is dark fiber, which is very wasteful of the fiber resources, or then you are going over to WDM and PON, and maybe OTN in some areas. But really, in high volume, we are looking at WDM and PON, and that's why PON is a very interesting technology to be used. Can deliver some scalability, can help us meet the stringent SLAs for latency and jitter in the network.
Great. Reza, how do you expect radio vendors to interoperate with BBU vendors when there are different options that have been proposed?
Yes, thank you for the question. So yeah, this is why it's so important to agree on these split options, right? You saw we had on the high level 7 split options, and when we broke out this option 7, there were even 4 actually split options under split 7. So that's why it's so extremely important, and really everybody in this ecosystem working hard to agree on which split options to take, so we can have the silicon and all the the various electronics and software, everything ready on time, and we can enable interoperability. So all these things are happening right now. Really exciting times to look at. People try to agree on major use cases. Obviously, operators, big players in that space, because at the end of the day, they pay the bills for all that here, and they bring their power there to agree on what are the major use cases we need to agree. And they are also obviously very interested to make the interoperability work between different vendors. And so all these factors contribute to, hopefully in near future, we have something where we have less options, less split options. I think we are seeing now that, at least from the 3GPP side, one split option on the high layer split is being defined. I think 3GPP is focusing on split 2. And now we need to hopefully agree also on split, lower layer split, on one that people can agree on. Lots of energy in that space on the lower layer split. eCPRI definitely put some stake in the ground from the vendors that are in eCPRI consortium, the top 4 that are in that consortium. They delivered their recommendation, but of course there are other vendors in this ecosystem. There are operators who have their own priorities. So it will be interesting to see at the end of the day which lower layer split option will become more successful, and it will be probably multiple of them, but it will be interesting to see beyond eCPRI what other lower layer split options become standardized, so that the vendors can more confidently and work on that and be sure that when it's designed, that will interoperate with the baseband units from other vendors.
Sure, great. Thanks so much for answering. I think we have time for a few more questions if you guys want to be sure to ask them. Which NGFI solutions will be deployed first?
So I think what we are seeing now is, I think NGFI 2, if you remember, and the topic that I was talking about here, maybe I just quickly go back to NGFI 2. So the NGFI 2 is the massive MIMO. It looks like this becoming very interesting because we are starting to see deployments for these massive MIMOs. So that could become actually an important one. The use case is there. If customers use NGFI 2 or use something else that's up to them. But the use case is already there, so I could see that that could take off. And certainly, when we look at some of these applications for mobile broadband in CRAN-based models, like the upcoming Olympic Games, this NGFI one could become also interesting. So those are the top two I see right now that could become very viable solutions and in near future in the next 1 to 3 years.
Terrific. So I think, do you see a role for high bandwidth Dario connection in combination with eCPRI?
So that would be high. I'm sorry, I didn't catch the high
bandwidth radio connection, I think.
Oh, okay. So I think, the question is coming probably from our audience that is interested in a radio connection as an alternative to using fiber over the link, basically. Okay, if that is the question, so this is also an interesting question. I think, so obviously the problem we have, just a quick background, is fiber, right? Most of what I talked about today is requires fiber. And fiber is obviously not something that can be put in place very easily. There are neighborhoods and geographies that don't have that advantage of placing the fiber. So it is very important to also look at solutions and use cases that can allow us to work with radio as the fronthaul technology, like formerly with microwave, right? So I think there could be use cases that could take advantage of radio as backhaul, and in fact, there are vendors that have solutions already looking into that. If that would be more the use case of this one, right? If you have wireless local loop and you put really an intelligent radio out there, then you could have a relatively lower bandwidth link, and that could be an alternative. If you have an area geography that doesn't have fiber, then you would use a radio type of fronthaul for the communication.
Great. I think we do have time for a few more questions from the audience. So what are the timing references and the measurement points, physical place in eCPRI and NGFI to do the measure for these time alignment errors?
Yes, good question. So this is when we go back to this timing measurement. So if you have basically here, let's start with this one, 65 nanosecond, right? So basically, you have a radio here that is in the neighborhood, and then you have a central unit somewhere farther away. So if first the test access point, typically if they use operators in that case, a dark fiber, or then the only test access point would be obviously here towards the central unit. Here you are on a pole, not a nice place to do measurements. Then you would do it at the central unit. You would need a tap splitter here at this location. If you have WDM or PON, then you can look into if they have ports available to perform that measurement on that. You would have still to remove that transponder or remove that fiber and perform the measurement from that WDM or OLT here towards the radio. That would be the test access point that you can do. So if you are measuring latency, you would be able to do the latency from here measurement towards the radio. If you're looking at performing a time alignment error or time error measurement, then as some of our audience knows, basically to perform that, you would need a good reference signal. So you would need to obviously know that there is either a GPS. If you have a GPS used at your radio, then you would also need a reference with the access to a GPS, and then you would be able to perform time error measurement. So availability of a reference source is important to be able to measure time errors for those measurements, especially when we get to that kind of measurement range below microsecond. Then we need a very good source and GPSs at both sides to make sure that we are measuring with the same reference, with same time of the day and same time and phase.
Okay, that's great. Do you have time for one more question, Reza?
Yes, I do.
Wonderful. All right. And thank you, everyone, for your questions. We will do our best to follow up after the webinar as well. Reza, how does virtual RAN fit into the emerging front haul and back haul? Wrap it up.
Yeah, so virtual RAN definitely very important from the perspective of when we look at emerging technology in applications in 5G and providing ultra low latency, massive type communication. We need such a low latency and massive scale that the current hardware-based, silicon-based approach will not scale nicely. That's why people look at network function virtualization into this virtual RAN. That is one of the reasons. There are many reasons for virtual RAN, but definitely there is a place for virtual RAN, and I think the applications for that would be more towards the central unit. When we get to this type of functionalities, to distributed unit, then the processing power, then the latencies and jitter we are dealing with are very challenging SLAs to meet for in the current technology with NFV. But when we get to this level of central functionalities, layer 2, layer 3 above, those become more things that we can deal with centralized with NFV type of infrastructure. So I definitely see actually a bright future actually for this type of virtual RAN applications in the future 5G world, and definitely a very interesting topic actually for another webinar, hopefully in future.
That's right, absolutely. Well, thanks again, Reza, and thank you everyone for joining us. That concludes our time today with VIAVI Solutions and RCR Wireless News. Please do stay tuned. We will be sending out an email later today with the PowerPoint slide presentation. Thanks again, Reza.
Thank you. Goodbye.